Yeah, good morning, students. Today, let us see about Mosfet. So, myself, Srinivas, working in the Department of Technical Education. So, before coming into the MOSFETs, first let us see what is the classifications of MOSFETs. So, MOSFETs are classified into two types. The first one is depletion type, another one is enhancement type. So again, depletion type MOSFET is classified into two types, that is P channel and N channel. So coming to the enhancement type MOSFETs are again classified into P channel and N channel. So let us see in detail what is meant by a MOSFET, what is a depletion type and what is enhancement type. So this is how an MOSFET looks like. So coming to the MOSFET is called as a metal oxide semiconductor field effective transistor. So this is one of the important semiconductor device which is widely used in all electronic circuits. So for example, if you take your motherboard or a mobile phone, most of the components are made by using MOSFETs. So MOSFETs are normally occupies very small in size compared to that of a BJT. This MOSFET occupies only 5% of space which is been occupied by the BJT. And apart from the size, the power consumption of this MOSFET is very less, since it has more advantages compared to other FET or BJT. This MOSFET is a widely used electronic component nowadays. Coming to the another advantage here, the MOSFET has a very high input impedance compared to that of a FET. This is one of the advantage of the MOSFET. And commercially compared to the FET, this MOSFET is used in all kind of electronic circuits. So whatever the circuit which uses FET can be replaced with the help of the MOSFET. So whatever the equations which are used for the FET can be used for MOSFET also. Next, coming to the MOSFET, it uses a metal gate electrode. So you know that MOSFET has three terminals. One is called as a gate, source, another one is drain. Gate, source and drain. So this is separated by a silicon dioxide layer.
There's no one in your contacts named Sharada. Whose contact info?
Sorry. And it uses an silicon dioxide layer to separate the gate here. So since this layer is separated by an oxide layer, it is called as insulated gate field effective transistors. So one of the advantage of this MOSFET is it can be operated in both depletion mode as well as in enhancement mode. So next, let us see what are the how the MOSFET is represented. So here, as we had seen, there are two types of MOSFETs. The first one is an N-channel MOSFET, another one is a P-channel MOSFET. So in the N-channel MOSFET, you can see here the arrow will be towards inside. In a P-channel, the arrow will be towards outside. Next, let us see what is the difference between a MOSFET and a FET. In the here there will be you will have only a single P region, and that we call it as a substrate. So a thin layer of metal oxide is which is deposited on the channel. So that we call it as an oxide layer, which is made up of silicon dioxide. So as silicon dioxide is an insulator, so therefore gate is insulated from the channel. So for this reason, MOSFET is also sometimes called as a IGFET, called as a insulated gate field effective transistor. First, let us see what is meant by enhancement MOSFET. See the diagram here which is shown is called as a enhancement type of MOSFET. So here this is called as a P channel enhancement MOSFET. It consists of a N type of substrate. This is an N type of substrate where two P type materials are doped, which are heavily doped, and these two things are called as a one terminal we call it as a source, another we call it as a drain. So a thin layer of silicon dioxide is grown over the surface of the entire assembly. This is silicon dioxide layer. So holes are cut into this silicon dioxide layer for making a contact with this particular P source and drain source. So here holes are cut into this particular P layer. One terminal will act like a source, another terminal will act like a drain. So on this silicon dioxide layer, a metal aluminum layer, this is a metal aluminum layer, is overlaid covering the entire channel region from the source to the drain. So this aluminum layer consists of the gate. So this terminal where aluminum is deposited, and this terminal we call it as a gate. So coming, as we had seen, one of the advantage, it occupies only very less space. So here the area of the MOSFET typically occupies only 5 square millis. So this area is extremely small, being only about 5% of the area compared to that of a BJT. So compared to that of a BJT, the MOSFET uses only 5% of the space. So here this acts like a parallel plate capacitor. You know, capacitor means two conducting plates separated by a dielectric. So here a parallel plate capacitor is formed with the metal areas of the gate, and this is a gate and this is the semiconductor area. And in between this you are going to have the insulated layer, we call it as a dielectric. So that acts like a capacitor. So a parallel plate capacitor is formed with the areas of the gate and the semiconductor channel acting as electrodes of the capacitor. So the oxide layer acts as the dielectric between these electrodes. So this silicon dioxide layer which is deposited here will act like a dielectric, and this aluminum layer will act like a conductor, and this substrate will act like a conductor. So two conductors separated by a dielectric is called as a capacitor and this MOSFET acts like a capacitor. So this is a symbol for a P channel enhancement MOSFET. So next coming to the working, the substrate will be connected common to the terminal, that is we call it as a, the substrate will be connected to the ground terminal. So a negative potential will be applied to the gate. Here you are going to apply the negative terminal. So that results in the formation of an electric field normal to the silicon dioxide layer. So which we can see here in this diagram. So the electric field originates from the induced positive charges on the semiconductor side of the lower surface of the silicon dioxide layer. So these induced positive charges becomes the minority carriers in the N-type substrate. So whatever you are seeing, this positive charge carriers, they become the minority carriers in the N-type of substrate. So this is a symbol for enhancement type of MOSFET. This is an N-channel enhancement MOSFET. So it consists of a lightly doped P-type substrate. Previously we used to take N-type, now we are using a P-type substrate where N-type of materials are diffused into the P-type substrate. Again silicon dioxide is coated on the surface, and onto that gate an aluminum layer is deposited. The same construction, but here you are going to use a P-type substrate. So it consists of a lightly doped P-type substrate into which two heavily doped N-type of materials are diffused. So again the surface is coated with a silicon dioxide layer, holes are cut through the silicon dioxide layer to make contact with the N type of blocks. So metal aluminum is deposited to the holes to form the drain and source terminals. So the surface area between the drain and source a metal plate is deposited, from which the gate terminal is taken out. So here from the N channel you are going to get the source and drain, and from this metal layer you are going to get a terminal, and the terminal we call it as a gate. So gate is insulated. This gate is insulated from the body, so we call it as a insulated gate field effective transistor. So coming to the physical construction, there exists no channel between the source and the drain. So there will not be any channel between the source and the drain. So MOSFET sometimes is called as a N-channel enhancement type MOSFET. So because a thin layer of a P-type material substrate touching the metal oxide film provides the channel for electrons. So between this N terminals there will be charge carriers. So it acts like an N type of material here. So these will be the minority carriers here. So here coming to the working of enhancement MOSFET, the drain is more positive. Here see, you can see in the diagram, the drain is made positive with respect to the source, and no potential is applied to the gate as shown in the figure. So the two N blocks which here you are seeing on the substrate, which is on the P-type substrate, will form like a two junctions, like we call it as a PN junction. So the two N blocks and P-type substrate form back-to-back PN junctions connected by the resistance of the P-type material. So these both junctions cannot be forwarded at the same time. So a small drain current which you are seeing here, both the junctions cannot be forwarded at the same time. So the small drain current in the order of few nanoamperes flows. So this is one of the advantage for the MOSFET. So if you want to manufacture a resistor onto an integrated circuit, this feature of the MOSFET is used. So MOSFET is cut off when the gate source voltage is 0. So this is why it is called as a normally off MOSFET. So coming to here, the gate is made positive with respect to the source, which we are showing in the figure. So a channel of electrons, which here you can see, is formed between the source and the drain region. So this is the source and this is the drain, and you can see a channel of electrons are formed between the source and the drain regions. So now it behaves like a capacitor with a gate metal. So this is a gate acting as one of the electrode, that is upper surface, and the other electrode is a silicon dioxide as a dielectric medium. So whenever a positive voltage is applied to the gate here, the capacitor begins to charge. So this is positive and this is a P-type substrate. So whenever you apply a positive voltage, the silicon dioxide layer will act like dielectric. So in turn, this N-channel enhancement MOSFET will act like a capacitor and it will charge. So consequently, this positive charge appears on the gate and negative charges appears on the substrate, right, in the substrate between the drain and the source. So here you can see the negative charge carriers which moves between the N channel onto the P-type substrate. So this N channel thus formed is called as an induced N channel, or we call it as a N-type inversion layer. So as here we see, as the gate to the source voltage increases, the number of electrons here in the channel also increases, which in turn will increase the drain current. So we'll see that as a gate source voltage. See, this is the gate and this is the source. So whenever the gate source voltage increases, the voltage which we apply between the terminals gate and source increases, the number of electrons in the channel increases, and which in turn will increase the drain current. So the minimum gate source voltage which produces the induced N channel is called as a threshold voltage. We represent it as a VGH TH. When VGS is less than VGS threshold, we say that the drain current will be equal to 0. So the drain current conducts only when the gate source voltage is greater than the threshold voltage. So for a given value of VDS and VGS is increased, more and more electrons accumulate under the gate and the drain current ID increases. Now we'll see it in the form of a graph. So the conductivity of the channel is enhanced by the positive bias on the gate, and the device is known as enhancement type of Mosfet. So the N-channel Mosfet can never operate with a negative gate voltage. So here as we seen in the previous slide, so these are the drain characteristics. So here the drain characteristics are plotted between VDS and ID. So VDS will be normal in the volts and ID will be in milliamperes, and these are the drain characteristics. So from here you can observe that the drain current has been enhanced on the application of a negative gate voltage. So this is the reason for calling it as an enhancement type of Mosfet. So by increasing the gate potential, the pinch off voltage that is on the substrate and the drain currents are increased. So the curves are similar to the curves which you had seen in the FET. So FET also will have the similar kind of drain characteristics. So next coming to the next one, enhancement kind of Mosfet. This is the symbol for a enhancement type of Mosfet. This is N-channel enhancement Mosfet. So this is a depletion Mosfet. So again we'll see the construction of a depletion Mosfet. So it can be same similar to that of a enhancement kind of Mosfet. Here you are going to have a P type of substrate. Here you have taken an N type substrate. Here you are going to take a P type substrate where N type of material is being diffused onto the P type substrate. So an N type of channel is obtained by diffusion between N type source and the drain in a channel in the N channel Mosfet. So here in the depletion Mosfet, a lightly doped N channel has been introduced. See in the diagram you can see the N channel has been diffused onto a P type substrate. So these N channel materials will act like a source and drain. So coming to the construction of this particular P channel depletion Mosfet. So depletion Mosfet may be fabricated from the basic Mosfet structure. So a P channel is obtained by diffusion between P type source and drain in a P channel Mosfet. So in a P channel depletion Mosfets are made by using a N type substrate and diffusing a lightly doped P type material, which will act like a source and a drain block. So these are the symbols of P channel depletion Mosfet, where you can see the arrow pointing towards the outside. And coming to the working of this N channel Mosfet, the previous we had applied VGS as positive. Here you are going to apply VGS as a negative. So here the negative operation of a depletion Mosfet is called, it is a depletion mode operation. So here you are going to apply VGS as a negative voltage. So when VGS is equal to 0, electrons can freely flow from source to the drain. Here which you can see in the diagram through the conducting channel. Since a channel exists between the drain and source, the ID flows when VGS is equal to 0. So it is also known normally we call it as a normally on mode. So whenever we are using Mosfet as a switch, this feature is being used. So next, when a negative voltage is applied to the gate, which you are seeing the figure the positive charges are induced in the channel by the capacitor action. So the induced positive charges make the channel less conductive and drain current increases, that is the VGS is made more negative, that is the gate to source voltage is more negative. So with negative voltage, depletion MOSFETs behave like a JFET. So when positive voltage is applied to the gate, free electrons are induced into the channel. This enhances the conductivity of the channel, so increasing the amount of current between the terminals. So since the action of negative voltage onto the gate is to deplete the channel, so the free n-type charger carriers, so named as a depletion MOSFET. So here you can see the characteristics of or we call it as a drain characteristics of a depletion MOSFET, where it is in depletion mode and enhancement mode. So whenever the VGS voltage is negative voltage, you can call it as a depletion mode. Whenever VGS is positive, you call it as a enhancement mode. So when the gate source voltage is 0, so considerable drain current flows. So when the gate is applied with a negative voltage, positive charges are induced in the N channel through SiO2 layer of the gate capacitor. Next, the conduction in N channel FET is due to the electrons, that is the majority carriers. So therefore the induced positive charges make the N channel less conductive. So the drain current therefore gets reduced with the increase in the gate bias voltage. So the distribution of the charge in the channel results in the depletion of the majority carriers. So that is why this type of FET is called as a depletion MOSFET. The voltage drop which you can see is due to the drain current causes the channel region nearer to the drain to be more depleted than the region due to the source. So this is similar to the pinch off voltage which we call in a JFET. Next, let us see the drain characteristics of depletion MOSFET. So the depletion MOSFET can also be operated in enhancement mode by simply applying a positive voltage, what we had seen in the previous characteristics. So application of positive gate voltage results in induced negative channel in N type of channel. So thus the conductivity of channel gets increased. So then N channel depletion MOSFET can be used as a enhancement mode by changing the gate voltage polarity. So when a MOSFET is operated this way, we can call it as a dual mode MOSFET. That is, whenever the MOSFET is operated in enhancement mode or depletion mode, we call it as a dual mode MOSFET. So next, let us see the comparison, like how the MOSFET is advantage compared to that of a JFET. So here the JFET is not insulated from the channel. From the MOSFET it is insulated. So for that sake we call it as a MOSFET is called as a insulated gate field effective transistor. So channel and gate forms two p-n junction. Channel and gate forms parallel plate capacitor here. There are only 3 leads here. You can see gate, source, drain, and another one is ground. So here you are having 4 leads. So it can be operated only in FET can be operated only in depletion mode, but whereas MOSFET can be operated in both depletion as well as an enhancement mode. So if you apply positive and negative voltages depending upon the voltage applied, you can convert the MOSFET into to operate in both depletion or enhancement mode. So here compare FET will have obviously input impedance will be high. Compared to that of FET, the MOSFET will have very high input impedance. Coming to the JFET, the signal handling capacity is less, and for the MOSFET, the signal handling capacity is more. Here the gate current is more. Here in MOSFET, the gate current will be very less. The fabrication is very complex and costly. And coming to the MOSFET, it is easily to fabricate. It is very cheap, occupies less space, etc. These are the advantages of MOSFETs. So coming to the advantages of MOSFET over JFET, the insulated gate in the MOSFET results in much greater input impedance than that of a FET. So whenever you want to consider both FET and JFET in terms of input impedance, you need to use MOSFET. Next, inter-electrode capacitance are independent of bias voltage, and these capacitances are smaller in case of MOSFETs compared to that of JFET. So it is easier to fabricate MOSFET than JFET. So here coming to the MOSFET has no gate diode, so this makes it possible to operate with positive or negative voltages. So coming to the applications of MOSFETs, because of higher input impedance, it can be used as a resistor in integrated circuits. So if you want to measure very low currents, we call it as an electrometer, which is used to measure low currents. So this MOSFETs can be used. MOSFETs are very small in size, which make them suitable for highly complex digital arrays. Right. Thank you.